Some further rules which will be obvious from your knowledge of derivatives would be something like the integral of cos x dx, right? The antiderivative of cos x. Well, we know that cos x is the result of the derivative of sine, so therefore the answer is sine over here, plus c, of course. Over here, if you have the antiderivative of sine x, we know that sine x is the derivative of cos x with an extra negative, right? The derivative of cos, we know that the derivative of cos x is negative sine x, right? So if I take the antiderivative of sine x without the negative, then that means it should appear on the resulting cos x expression and then plus c. Okay? Because if I took the derivative of negative cos x, the negative would be bypassed. The derivative of cos x is negative sine x, and two negatives would then cancel, giving me the original sine x here. Okay? So a lot of the antiderivative processes will just have to be a little intuitive from your knowledge of the derivative processes you're already familiar with. Otherwise, you'll end up memorizing or attempting to memorize a giant list of rules that are pretty obvious if you just use inspection. For example, let's try a couple more complicated looking expressions. If I were to find the antiderivative of secant squared x plus x cubed plus 5, let's make another power function, 5x to the 4th, something like this. A little more complicated. Okay, so using the sum difference property of the antiderivative symbol here, the indefinite integral symbol, so this should be the same as antiderivative of secant squared onto itself plus antiderivative of x cubed onto itself plus antiderivative of 5x to the 4th by itself. And then we can apply the constant multiple property to remove the 5 off of the x to the 4th to the outside of the integral symbol. So we would have integral of secant squared plus integral x cubed plus 5 integral x to the 4th. Now each of these has its own particular rule. Even though I didn't state it before, we do know, I didn't state a lot of rules because, again, you should be able to realize them more intuitively than from memorization just by your knowledge of derivatives. So we know that the derivative of tan is secant squared. So now we just think backwards. So the antiderivative of secant squared must be tan. Okay? Just thinking backwards a little bit for these types of problems. So this is tan x. Now, although I'm taking the antiderivative of secant squared right now, it would make sense to put a plus c here. But I know I'm going to get a plus c from this one and a plus c from this one, which are not necessarily all the same. And those would just all combine, right? I would just be adding 3 constants together to get one more constant. So anytime you're doing a problem like this, you're only going to introduce one constant symbol at the very end of the problem. So I'm not going to put a plus c on the tan x here. All right. The x cubed, I need to raise the power by 1. So x to the 4th. And I need to divide by 4, right, the new power. But I'm going to write it as 1/4 out here. I like to write like that. Not everybody, it's your choice. Not everybody likes to do it this way, but I do. So I'm going to write 1/4 x to the 4th. And now I have plus 5 times the derivative, sorry, times the antiderivative x to the 4th. So that should be very similar to this structure here, 1/5 x to the 5th. Okay? Now I'll put the plus c to complete the general antiderivative here. Now I'll just combine 5 and 1/5 into 1. So we have our answer as tan x plus 1/4 of x to the 4th plus x to the 5th. Okay? Something like that. Take another example. Let's say you have the antiderivative of, let's see, we'll say 5 on x squared plus 3 on x minus e to the 2x. Get some more variety in here. All right, so we see some power rules here, it looks like. Now, one of these is a true power rule and the other one is not. Right? This is not really a power rule going on here. We can certainly first apply the sum difference property and the constant multiple property. I'm just going to do them simultaneously, right? So this 5 is a constant multiple on 1 over x squared is the way I'm going to think about it. Okay? So I'll have 5 1 over x squared dx plus 3 1 on x dx minus e to the 2x dx. Okay. So that was the use of the sum difference property. The integral symbol applied itself to each of these three separately, along with the dx corresponding always. And at the same time, I removed the constant multiples of 5 and 3 from these two functions, the variable part of these two functions. All right. Now I'm going to rewrite this one as x to the negative 2, so I can see it more clearly as a power rule. So just like I do the same thing when I want to take derivatives, I rewrite these quotients as negative powers. I'm not going to rewrite this one, though, because this is not really a power rule going to happen here. This is going to be the natural log result that was mentioned a minute ago. And then this last one here, e to the 2x, will take a little more thought, but not too much. Okay? I can't just say it's e to the 2x, all right, as the antiderivative. All right, going back to here, take care of the easier ones first. We'll have 5. The power has to go up by 1, so I now get x to the negative 1, and I'm going to multiply by the reciprocal of that. That's what I've always been doing. I didn't say it that way before, but you're just multiplying by the reciprocal. Like that. Which of course is just negative 1, but I just want to write it in the formulaic way to illustrate that. All right, so now you have 3. This was a rule that you should just memorize in cold, and that is, it's the natural log of absolute value of x. Okay? And over here, I'm going to think a little bit. We know the exponential function will come back. So e to the 2x is here, but that's not the totality of it. So the way to deal with these kind of situations is to think a little bit about if you had the derivative, all right? This is our supposed antiderivative. So starting with it, if we took the derivative of e to the 2x, we would get 2e to the 2x. We do not see 2e to the 2x sitting here. We only see e to the 2x. So therefore, I need to compensate for that. So what I should do is divide by 2. Okay? And that makes perfect sense, because now if I take the derivative of this, instead of just e to the 2x itself, but the derivative of 1/2 e to the 2x, the derivative would bypass the 1/2, it would be left there. The derivative would apply itself to e to the 2x, leaving us an extra 2 on the outside. The 2's would cancel, leaving us with the original integrand. So this must be the antiderivative of e to the 2x. And I just slap a plus c on the whole thing. Okay, so now we have, simplifying this just a little bit, and it's just one piece here. I have negative 5 on x plus 3 ln magnitude x minus 1/2 e to the 2x plus c. And so we have another rule that we've kind of thought about here that we can now write out. So there's our answer to that problem. We can also state more definitively that the integral of e to the kx is going to be 1 over that value, right, the coefficient on x up in the exponent, times the original. Okay? So there's another rule to keep in mind if you ever come across something more complicated than just e to the x. If it's just a coefficient on the x, then just divide up by that coefficient on the antiderivative.